Hello, this final video about Möbius transformations is when not to use the geometric method. First example is if you're asked to find the locus, the path of z, which is governed by that equation. And you can do that very easily without having to do any geometry or really any algebra. Because what that's saying is the distance of z from 1 is the same as the distance of z from 2. So, here's 1, here's 2. Z is all the points which are the same distance from each. So it's that point, for example, and all these points down here, and all these points up here. It's a straight line halfway between the 2 points, or the perpendicular bisector, and you can draw it and then you can find out what its algebraic formula is. Right, suppose however it's like this. Now that's not quite so simple, so I'm going to show you 3 methods of doing it and you choose which you think is best. The first is just the algebraic method. You square up each side. So this gives you x plus 1 squared plus y squared is equal to 4 times x minus 2 squared plus 4 times y squared. So 3x squared minus 16x on that side. So minus 14x by the time you've taken that away, plus 3y squared plus 4 times 4 is 16, minus 1, 15 equals 0. And that's a circle, and you can do a bit of algebraic simplification of that to find out what the centre is and what the radius is. That's one method. Second method is to adapt the geometric method I showed you and say, well, look, this is path of z when w equal to z minus 1 over z minus 2 has mod of w equals 2. So it's a, you know what the path of w is and you want to find out what the path of z is. You can do this by the same method as before. Draw the path of w, the locus of w. Draw in the pole. Now the pole now is going to be when z is infinity. So it's going to be when z is infinity, the minus 1, the minus 2 you can ignore. So w is 1. The pole is there. The w diameter ends in line with the pole at there and there at 2 and minus 2. So w diameter minus 2 and 2. Z diameter. Right, we've got to work it out backwards. 1 is when 2 minus 2 is equal to z minus 1 over z minus 2, which gives you z equals, well, gives you 3z plus 4 plus 4 plus 5 equals 0, or z equals 5/3. And the other one is when plus 2 equals z minus 1 over z minus 2, which gives you plus 2z z. Minus 4 plus 1 is minus 3, or that equals 0, or z equals 3. So that gives you the ends of the z diameter, and from that you can work out you can draw the z circle and work out its centre and radius. You see it's a little bit more complicated here because you find the w values easily enough, but then you've got to solve that equation rather than just plugging in numbers. So there is a third method here. Right, this third method you would have depends on, again, on a geometric theorem, and you would have to name this geometric theorem, and it's called the circle of Apollonius. Circle of Apollonius, that says if you have 2 points, here they are, 1 and 2, and you take the locus of all the points which are a fixed number further from one point than from the other, so every point here is twice as far away from this as from that, then that path is a circle. That's why it's called circle of Apollonius. And then by symmetry you can say that the diameter of the circle of Apollonius must be the 2 points on that line where that relation is true, which are 2 points which are twice as far away from 1 as they are from 2, which are 3, which is 2 units away from 1, and only 1 unit away from 2, and the other point is going to be 5 over 3, which is 2/3 away from 1 and 1/3 away from 2. So again, you get a circle with diameter between these 2 points, 5/3 and 3, and you can calculate all the equations of the circle from that. You can do it that way. What you have to mention if you do that is circle of Apollonius.